Today, I'm going to talk about something very important in large language models called tokenization. When you have a data set for training or fine-tuning, you need to transform it into something that can be consumed by the large language model. You need to turn the text into numbers. So tokenization is a bit more involved than simple vectorization, but leads to the same overall result. Input text, vector output, and the ability to encode and decode. Your tokenization strategy isn't just important, it's vitally important for every subsequent step. Let's have an example. This is a comparison between GOT 7b and GPT-4 in math and arithmetic. As you can see, this is the prompt, and this is the output of GOT, and this is the output of GPT-4. This is the correct answer. GOT 7b consistently outperforms GPT-4, which leaves the question, why does GOT perform better despite being 200 times smaller? It is because of the tokenization algorithm used. The GPT family of models tokenizes all subwords and digits in groups based purely on frequency only, meaning that if that exact group of numbers of words hadn't shown up before, they could be grouped together during the embedding and inference processes later. GOT is a fine-tuned llama model, meaning that while it was fine-tuned on math to be good at it, the underlying secret to success lies in its tokenization strategy, which is the same as Llama's GPT-X tokenizes like this. Print the encode, this is the number minus this number. Notice how the first group of numbers is 7 digits, but the entire output is 8 tokens. This is the exact grouping methodology we are talking about. Compare that to Llama tokenization strategy. Notice that each digit is highlighted. That means the model will eventually see all the digits. This example demonstrates your tokenization strategy will ultimately determine what your model will see and won't see, as they will become tokens, and that's why it's vitally important to get it right for your use case. Tokenization essentially consists of two major steps: step to split up the text and step to turn it into numbers. Here are examples of all the current popular options for basing your tokenization. Word-based, like Muhammad Ali becomes Muhammad, Ali in a list. Character-based, like Shakespeare becomes, as you can see, character by character. Subword-based, like this sentence, the quick red dill fox jumped over the lazy brown emolga, becomes the quick red delf ox. Notice here the algorithm splitted delf into two tokens, delf ox into two tokens, delf ox. Jumped as well is splitted into two tokens, jump and ed. Three main algorithms are used to create the subword dictionaries. BPE, which stands for byte pairs encoding, word piece, and unigram. Now let's see how we can train a custom version for both BPE and sentence piece on your data so that you're equipped to face almost any dataset heads-on. You will want to tune three key parameters: vocab size, min frequency, and special tokens. A large vocabulary size means your tokenizer will be more robust and will likely be better at handling more languages. but it will add computational complexity. Minimum frequency determines how often a particular subword token has to be seen in the dataset before it is added to the dictionary. Larger values prevent rare and likely unimportant tokens from filling our dictionary. Lastly, special tokens are relatively straightforward and include syntactical tokens we care about specifically for model training. Here you use this code to mount the drive on your Google Colab so you can have access to the folders. The text of Mary Shelley's Frankenstein can be downloaded from this link, so you can upload this into Google Colab directory. In summary, this code loads your training data and trains two subword tokenizers, byte level and sentence piece, then saves them to disk, reloads them, and wraps the sentence piece tokenizer in a Hugging Face compatible class, finally demonstrates tokenization and encoding. Let's have a look. So this is the first step to load your data. Here you can replace it with the directory that you saved the text file into it. And as you can see here, this is the byte level BPE tokenizer. Here we begin to train the tokenizer. We added the path to the files if you have multiple files, for example. This, I want the vocabulary size to be 52,000 and the minimum frequency to be 2. So the special tokens, the S, the pad, and this is the end of the sentence, unknown UNK, and the mask token. And here I specified the output to be inside tokenizers byte level BPE. Here to load the pre-trained tokenizer by reading these two important files, which will be generated after this step. So this is the merges.txt. This G dot means white space in this tokenizer. And the vocabulary.json, for example, the start of the sentence will have this ID 0, and the end of the sentence is 2, and so on. Let's have an example. This sentence is getting encoded by a tokenizer. And let's print the tokens. If you run this cell, you will have this output, this, and this G dot means a space before this word. So space, white space, sentence, white space is white space getting, white space encoded, and so on. And to have a look at the IDs, because large language model will deal with these IDs. It doesn't understand the tokens, the words. It will deal with these IDs by using .IDs. Now I will show you another algorithm or another tokenizer, which is sentence piece BPE tokenizer. There are some differences. For example, if you run this cell, with the same sentence, you will have the output like this, underscore this. Underscore means the beginning of the word. So this is the beginning of the word, this, then sentence, this is the beginning, and it split it into 3 tokens. And to have a look at the IDs, you can use tokenizer.encode with the example text. So we initialize the text to train from, then train a byte pair encoding tokenizer, then train a sentence piece tokenizer, and then set the token for all special tokens. then saves for later use. You can use this tokenizer in any project you want to deal with large language model. So all in all, tokenization loses information, just as converting from speech to text does, namely word order, syntax, and meaning, semantic. All of the information about what a number is and how it would differ from a letter is completely gone after tokenization. To circumvent potential semantic and syntactic problems, we need to create an approximation for each of these features and figure out how to mathematically represent them in abstraction to insert that meaning back into the tokenized vector. For this, we have embeddings.